This may be familiar to most of you, right? So matter is anything that's going to occupy space, right? So anything that occupies space. In general, since chemistry is the study of matter, we're looking at stuff that occupies space, and this boils down to how do electrons in atoms and molecules behave. Right? The nucleus of the atom is still considered part of matter, but once you kind of start studying the nucleus, you kind of move from chemistry and you're kind of going into the realm of physics. So chemistry is usually the study of how the electrons in atoms and molecules behave and how these electrons repel each other. And we'll talk about what the electron is in more detail in a week or two. And how they repel each other is how we, kind of feel matter, right? When you press your hands against each other, it's really the electrons that don't allow your hands to pass through each other. The electrons in the atoms of your thumb repel the electrons of the atoms in your other thumb. And so we generally classify things into three types of matter. We talked about this the first day of class too. There's more beyond that, but what we're focusing on are these states of matter, right? We have solid, liquid, and then gas molecules, right? And these all have to do with how close these molecules are to each other. And so the way we define a solid is a densely packed particles with a definite shape and volume. What does that mean? So solids aren't something that's flowing, right? So whatever shape they hold, they keep that shape. So they have a definite shape, right? They have a definite volume because that shape doesn't expand or contract into a larger volume. And so this solid particles also have strong forces of attractions towards each other. Right? You can rationalize that they have strong forces of attraction because the atoms and molecules are so close together in solids, right? This is because this makes it so that the atoms and molecules in solids are close to each other and don't move. And I'll put that in quotations because they don't move, but everything moves technically, right? So they don't move much. And solids are also not very compressible, meaning if you try and compress a solid like this table, it doesn't compress very much, right? And that's because the atoms are already so close together, they don't really have much room to compress. And the way we define them again is that they have definite shape and volume. Other things that you might see commonly in solids is they can be conductive of heat and electricity. Why? Because they're so close to each other that electrons can bounce between these molecules and atoms. All right, everyone good on that one? Good to go on? Okay. And so liquids are loosely packed particles, and this still means that loosely that they're still relatively close. And so if we think about a solid as having definite shape and volume, how do you think a liquid will compare to that? Do you think a liquid will have a definite volume? Yeah, right, because otherwise all the measurements I had you guys take last week and what you'll be taking today wouldn't make any sense, right? They have to have a defined volume. So they have a definite volume or defined volume. Well, what about their shape? Do we think that liquids have a defined shape? And so what indicates that they don't have a defined shape? What shape do they usually take? Whatever container they're in, right? So they take the shape of whatever container they're in, which means that their shape is not well defined. Right, so an undefined shape, right? They take the shape of their container. And so liquid particles generally still have relatively strong forces of attraction, but they're not quite as strong as solids, right? Because they're still close to each other, but they can move past each other, right? So they have, we'd say, moderate forces of attraction. Really, these, kind of adjectives we use to describe them. Really, it depends on what you're comparing it to, right? Think about, well, how strong are these forces? Well, compared to, gas particles, these are really strong forces, but compared to the center of a black hole, maybe they're not so strong, right? So whenever we're looking at comparisons, it matters how we're comparing things. Relative to solids, they have moderate forces of attraction. And these are going to be slightly compressible. Generally, if you have a Erlenmeyer flask full of water and you try and put a piston in there and compress it, it's still going to be pretty hard to compress, right? So these are only going to be slightly compressible. And what we mean when we say compressible is like if you squeeze it, does the volume itself change? They're pretty close to each other, so the only thing that might happen is you might, if you have water and if does anyone know what happens if you compress it enough, what happens? What about CO2 gas? Does anyone know what happens if you take carbon dioxide gas and you compress it really, really hard? Okay. So it can explode if you get it to really, really, really high pressures, and if you release it fast enough, it can explode. Has anyone done the experiment in any previous schooling where you make ice cream? What? Where you make ice cream? Does anyone know what you use to make ice cream in class usually? Yeah, you use dry ice, right? And dry ice is basically just carbon dioxide that's been compressed. So if you start compressing things, they will eventually turn into the other phase, right? So if you go from a liquid and you compress it enough, it will eventually turn into a solid if you add enough pressure. And we'll talk about that more in the next lecture. But yeah, also if you do a solid and you compress it a lot, so if you've seen, what's that on Instagram guy, he does the hydraulic press channel. Has anyone ever watched that? That's a lot of fun, right? So if you get something that has a lot of energy in it, like a solid, and you compress it, it will explode because you're putting so much pressure on those bonds that they break and they release some energy. Okay, so liquids have defined volume but undefined shape. So gas particles probably have what shape and volume? They're undefined, right? Because these are going to have very weak forces of attraction to each other. And so if you have an Erlenmeyer flask full of gas, you can't keep the gas in the Erlenmeyer flask, right? It's just going to move away. It has no defined shape because the gas molecules don't really feel each other. The volume, right, so you can't measure them in an Erlenmeyer flask, and the shape are both undefined for a gas. And so gas particles have weak forces of attraction, so weak that for most of the equations and stuff that you see for gas molecules, you basically assume that they don't feel each other at all, right? You just assume that they never interact with each other. It makes the math really easy to deal with, and it gives us a lot of really important results. And so that's one of the ways we kind of simplify the world around us. We say, well, these forces are so weak we don't even care about them. And pretty much most standard chemistry practices deal with that assumption. Right, so if we had, kind of just reviewing, the properties of solid, liquids, and gases, solids had what kind of shape and volume? Defined. And the particles, were they close or far apart? Close to each other. And so if you were to think about something like a physical property like density, how do you think the density of a solid compares to the density of a gas? Yep, it should be more dense, right? If we have a given volume, of a material and the particles are closer together, there's more atoms or molecules in that volume, so it should be more dense, right? Density also increases as we go up this chart. So increasing density. Liquids, we had no defined shape because they took the shape of what? The container. But we had a defined volume, right? Because we can measure the volume of a liquid because the molecules are still relatively close to each other. And but they're mobile, so they can move around. And then gas had no defined shape or volume. and no defined volume. And the particles for gas were very far apart from each other. And we, like I said, with a lot of the equations we'll use in this class, we often assume that they're so far apart and the forces are so weak that they don't interact with each other at all. All right, so let's take a 5-minute break. When we come back, we'll talk about the different classifications of matter and for mixtures. See if we can finish up classification of matter. So this is a relatively short lecture. Right, so our matter is going to be anything that has mass or energy. We can have two different categories for this. We can have mixtures, which are going to have variable composition and properties. And then we're going to have pure substance, which are going to have fixed composition and properties. All right, so mixtures versus pure substances. And so mixtures can be converted into pure substances by simple physical processes like filtration and evaporation. Right, so has anyone taken ocean water and boiled it? I don't know why you might do that. Has anyone tried it before? Or has anyone gotten some ocean water? Actually, or even if you just get out of the ocean, right, and you don't, let's say you don't rinse off, you just keep all that ocean water on you, right? And if you after a while, what's left over on your skin? Salt, right? And so that's purified, separation, going from a mixture to a pure substance by evaporation, right? You have this mixture of salt and water on your skin. You didn't wash off before you left the beach, so you got your car all greasy and stuff. And then it evaporated away and left the salt on your skin. So that's a physical process by which you can filter a mixture into a pure substance. The other ones, you think about like a soup broth that has, pasta noodles or rice or something in there. You can turn that into a pure substance that has a fixed composition by just taking a sieve and filtering the soup over that, right? And whatever solid is left in the sieve and whatever is liquid goes through, right? So the liquid has a uniform property of being a liquid. The mixture has variable properties, right? Because you think about, does it have defined shape or volume? Well, parts of it had defined shape, the little pieces of rice in there or pieces of pasta or vegetables. Those have a defined shape, but they don't, and defined volume, whereas the liquid doesn't have the defined shape, right? So that's what it means when it says variable composition and variable properties. And again, these can be converted between each other by simple physical processes usually. All right, any questions on it? Anyone still writing? I don't want to go too fast. All right, so pure substances, these have fixed composition properties. These can be divided into two different categories. We can have elemental, so elements, in parentheses I'll put elemental, because I'll go interchangeably between those two. These are going to be composed of a singular type of atom, or you can have compounds. Compounds, are the same thing as molecules, usually, right? So these can be two or more elements that are going to be chemically combined. So in salt water, for example, if we have the individual water molecules, does anyone know the chemical formula for water? H2O, right? We have 2 hydrogens and 1 oxygen. That's classified as a compound. Why is it classified as a compound? Well, it's still a pure substance because it's water, but we have 2 different atoms that are bonded to each other, right? So that's a compound, a molecular compound. Elements, these are going to be composed of 1 type of atom. So if we look at something like hydrogen gas or pure gold, depending on the carat, then those are going to be elemental compounds, right? But that doesn't necessarily mean they can't be molecular, right? So some elements, like hydrogen, oxygen, nitrogen, what else? Bless you. Fluorine and chlorine, those are all going to be elements that when you find them in nature, they're actually going to be in what we would say the diatomic form, meaning the same way water is H2O, hydrogen is going to be found as H2, right? So it's going to be a molecule, but it's still going to be pure hydrogen, right? It's still pure hydrogen because it only has hydrogen in it, but it's still going to be a molecule because there's 2 of them that form a little compound together. All right, so that's how we separate elemental compounds and, elemental substances and compounds. And these two can be converted into each other through chemical reactions, right? So this is actually changing the bonds, breaking and forming bonds to form new molecules or elemental compounds. So if you have a compound, sometimes you can react two compounds together, and then you get elemental substances. Or you can go the other way, you start with multiple elemental substances, and you end up with compounds. But the important part is that these are going to be chemical processes or reactions. So for example, electrolysis is here. This is something that you can do by running an electrical current through water, and it'll split water molecules, one into hydrogen gas and the other one into oxygen gas. So it takes a compound and makes it into an elemental substance. Okay, any questions on that? Anyone still writing? I see some people writing them. So those are pure substances, and then we also can classify different types of mixtures. All right, so we can have two different types of mixtures, right? So these are going to have variable composition and properties. There's going to be heterogeneous mixtures and homogeneous mixtures, right? So these homogeneous mixtures are going to have uniform composition and properties. That would be an example of salt water, right? When it's in the ocean, the property of a liter of salt water is the same as another liter of that same salt water, right? That's because the composition is uniform in the sense that the water and all the salt is all going to be in the same phase. So all components are in the same phase, and what I mean by that is the same physical state. All right, so if the water is in a liquid state, that means that the salt that's in the water is also in that same liquid state. A heterogeneous mixture is going to be something where the components of that mixture are not in the same phase. That's something like salad dressing or cement, right? In the or soup, for example, right? The soup, we have liquid broth and then solid vegetables. Right, so these are going to not be in the same physical state. And when I say these, I mean the components of whatever are in the mixture, right? So salt water, we have salt and water together. Ink, you have ink molecules that are mixed with water molecules to actually make the ink. Tea, for example, is water with then diffused particles from the tea leaves, right, or diffused molecules. So those are a mixture, and they're a homogeneous mixture because they all exist in the same phase. The heterogeneous mixture, they're not in the same phase. All right, any questions on that? All right, so here we have just a pictorial example. So you have each of these substances below. Classify it as an element, compound, or a mixture. And so the colors here mean different atoms. So for example, purple could be hydrogen, yellow could be oxygen, for example. And how are we going to classify this substance? Is it an element, a compound, or a mixture? All right, so here, are these different atoms or the same atom? Same, right? So that should be an elemental substance, right? Because we have all the same atoms there. We can have something that is still a mixture or a pure substance. Sorry, not a mixture, a pure substance. But it's only different if it's comprised of molecules with different atoms in them. Right? And then the second one, what is that? Is that going to be elemental, compound, or a mixture? So it's also an element, right? So remember those elements I said, hydrogen, nitrogen, oxygen, chlorine, and fluorine? Those ones you find in nature. They're the same atom because of the same color here, right? These are the same atom. You just find them as a molecule naturally, right? So there's two of them that are going to be bonded to each other. So this is also going to be an elemental substance. Why? Because all of these are the same atom. What about the next one? Is that a mixture, compound, or an element? A compound, right? Because it's still all composed of the same molecules, but each molecule has different elements in it, right? So this is going to be a compound. And what about the last one? Is that an element, compound, or a mixture? This is going to be a mixture, right? And if they're all in the liquid phase, we would say that that's what kind of mixture? Homogeneous or heterogeneous? Homogeneous, right? They're all in the same physical state, so that'd be a homogeneous mixture. You can't tell that just by looking at this, because that's just me asking you on top of what's there. But this would be a mixture. Why? Because it has different elemental components to it, different molecules and elements mixed together. All right, and so it's a mixture, but if it's the same phase, then it would be homogeneous mixture. But if it was different phase, and again, phase I'm just using interchangeably with physical state. Summer?
So let's say the pink and yellow was bonded to the example, the third example.
This one? So if they were all bonded to each other?
All bonded, it would still be a compound.
It would still be a compound because it's all one molecule that exists here, right? So they have to go through a chemical process to break that up. But they would all be the same molecule. It's like a thing of water, except you'd have a much more complicated molecule.
Okay.
Yeah, good question. Different phase. That would be heterogeneous. Okay. All right, am I writing? Right, so just to reiterate what I said, heterogeneous mixtures are non-uniform in their composition, meaning that they have different elements in different phases of the mixtures, right? So that includes like vegetable soup, cement, and salad dressing. Does anyone else have an example of a heterogeneous mixture? So we'll think of something like really weird, like Aiden, I know you're talking about your car earlier, a catalytic converter on a car, right? Is that converts gas molecules into less polluting gas molecules. Those two, even though you don't think of them as being mixed with each other, right? You still have a solid thing that exists in a gas, so that's technically a mixture. That would be another heterogeneous mixture, right? So that'd be like a catalytic converter for a car and carbon monoxide or something like that. Carbon monoxide, CO, right? So that's also a heterogeneous mixture. And so you'll find with these definitions a lot of times that, they're very, very broad, right? So some things that we wouldn't consider a mixture in how we think intuitively, in the definition in chemistry, those would be considered a mixture. All right, and then homogeneous are uniform in their composition, which means they exist in the same what? Same physical state, or same what? Physical state or the same phase. I just think phase sounds a little bit cooler, so I like to say that. So these would be things like gasoline, soda pop, and salt solution, right? However, you can have a heterogeneous salt solution mixture, right? Or coffee and sugar. And so when would those be a heterogeneous mixture? When it's not dissolved. So if it's a really cold solution or something, you can get all of the salt to crash out. Now you have physical salt particles and liquid water around it. Those are not the same phase anymore, right? So those can be, I'll put a little asterisk next to that, at an appropriate temperature, right? And that's our homogeneous mixtures, right? And so then we can also characterize matter by their physical and chemical properties, right? So the characteristics of a substance are called as properties. So this is an example that we already talked about, something like density, right? You can have a compound of molecules that are bonded to each other as a solid, liquid, or a gas, and then we have a defined density for that material, right? Physical properties are those that describe matter without changing its composition, right? Does anyone have an idea of a physical process? Right? What can be a physical process where we something is happening but we're not changing its composition at all? Evaporation, right? So evaporation, example, evaporation. We're going from liquid water to, second, my pen froze, to gaseous water, right? Oh no, it's not my pen, it's the iPad. I don't think this battery should be fine. All right, it goes to gaseous water, right? You're not changing the composition because you're going from liquid to gas. You still have the same water molecules, right? It's just they're in a different physical state now. So that's considered a physical change. Let me check the battery for this. All right, and then we have chemical properties. So these are the characteristics that describe how elements are going to behave in combination with other matter, right? And so these fall under the umbrella of, all right, it's working again, of chemical reactions. So an example of that is a catalytic converter making carbon monoxide go to CO2, right? Carbon monoxide, pretty terrible. CO2, not as bad. Or we're changing the chemical composition because we're going from a molecule of carbon monoxide to carbon dioxide. So we're changing the composition. And we describe these things differently. We describe evaporation, that's a physical change, and chemical reaction, that's a chemical change. All right, so if we have each of these descriptions, so I'll give you a second. Next slide will have each of these descriptions. You describe, is that a physical property or is it a chemical property of that material? All right, so here we have some examples. Oxygen being a gas, is that a physical or a chemical description? Physical, right? We're talking, and we think of that, that's the physical state of matter, right? That's the phase that it's in. This will be physical. What about helium is unreactive? That's a chemical property, right? Meaning that it does not like to react with other elements. So this describes how it interacts with other matter, right? So this is a chemical property. And some of these we'll talk more in detail as we go over them. So water has a high specific heat, right? What is specific heat? That says how much energy does it require to heat up a gram of water, for example. So water has a high specific heat. What do you guys think that is? That's a physical property of water, right? That doesn't change when we're not thinking about how that reacts with other matter. We're thinking about how does that interact with the physical world around it as we change the temperature of water, right? So this is a physical property. What about gasoline being flammable? That should be chemical, right? So we'll learn that when something is flammable, it undergoes a combustion reaction. It reacts with oxygen to then make some other molecules, right? So we're saying, how does this react with oxygen? So this is going to be a chemical property. And what about sodium is soft and shiny? So if you actually did get a little bit of just pure sodium, it's very soft and it's very shiny. That'll be a physical property, right? Shininess and how malleable a piece of material is, that's an inherent property of that elemental substance. So this is a physical property. Okay, so these are the properties of specific elements. Is it a chemical or physical property? We can also look at changes. You know, are these going to be chemical changes or are they going to be physical changes, right? And so this is, again, how are we changing the compound in any way by breaking or forming chemical bonds? So cooking food, is that going to be a physical or a chemical change? So what happens when you overcook food? It burns, right? And that's also inducing a combustion reaction. So if you're not good at cooking food, it's physical, or if you're not good at cooking food, then it's chemical, and if you're good, it's a physical change. But no, in general, cooking food is usually a physical change. We're undergoing a chemical reaction to change some of the materials. Like if you want anything to have that nice, crisp to it, then generally you want to cook it a little bit more. You want to combust the outside of the food. So this would be a chemical change. What about mixing sugar and tea? What do you guys think? This one's a little challenging to think about, right? So if we mix sugar and tea, so let's make it a little simpler. We don't have to think about tea. What about just sugar and water, right? Remember when we're going between like mixtures and pure substances and stuff, if it's a physical process, we can isolate them, right? And with the salt water example, when the water evaporates, what's left over? Salt, right? And so what we would say is that that's a reversible process. And usually physical things are reversible. It's easy to reverse, dissolving salt in water because you just evaporate away all the water. Whereas it's hard to reverse turning carbon monoxide into carbon dioxide. We probably have to put a lot of energy into that happening. So dissolving stuff and then evaporating stuff away, that's considered a physical change. What it means is that you have something solid, and when it gets dissolved, it gets moved into the, what we would say, aqueous phase, so it's a dissolved phase. In that dissolved phase, it's still the same molecule, it's still the same sugar molecule, still the same salt molecule, it's just surrounded by a lot of water molecules. So this is a physical change. So that one's a little hard to think about. When we talk about dissolving stuff, solubility and things like that, it'll make a little bit more sense. But that's a physical change because if we have a sugar molecule, and sugar molecules are usually pretty big, complicated molecules, right? Think about glucose, fructose. Have you guys ever seen those pictures of what a carbohydrate looks like? Long rings attached to each other. They're pretty big molecules, so those don't break up. You don't break up those molecules when you dissolve them. They just get surrounded by water molecules, and so they can mix with them. What about melting ice? What do you guys think that's going to be? That's another physical change, right? Because we're not changing the specific water molecules. We're just going from what phase to what phase? Solid to liquid, right? So that's a physical change. And what about burning gas? What do you guys think there? That's going to be a chemical change. Again, combustion is what we're looking at there. Chemical change. And this last one's kind of hard to think about too. What about food molding? So technically, usually food molding is some fungus or bacteria that's there digesting the food, and it's making it undergo chemical reactions, right? So that would be a chemical change. And what about, not my favorite example, but this one, if you think enough about, you could argue both. If we're chopping wood, for example, that's what I would think too, right? Physical changes. I didn't even know how chopping wood could eventually become a chemical change. So if the tree is alive, yeah, and then maybe you're cutting off some biological pathways. If you put it in a fire, that'll make a chemical change. And so the one that I heard is that eventually if you just keep cutting smaller and smaller and smaller and smaller pieces until you get to the atoms, then you start breaking the bonds of the wood molecules apart, then eventually it becomes a chemical change, right? Once you start changing the bonds of the wood, then it becomes a chemical change. But yeah, those other things, burning wood, breaking up biological processes that are going on in the tree, those would also be considered chemical changes. All right, so that's how we classify matter, and then we did a little bit of classifying of changes in matter as well. Okay, so I think that's what we'll end off for the classification of matter. This is kind of, we're just looking at matter and changes and seeing if we can identify what's going on. Probably for the rest of the lecture, what we'll do is we'll spend a little bit of time talking about temperature, heat, and energy, and that's related to changes in matter, except now we're going to start going from talking about things qualitatively, by observation, into more quantitative analytical approaches to what does a change in matter mean. Okay, so